Quick sound check. Quick sound check. Quick sound check. Quick sound check. Perfect. I'm just setting up the last few things here, but I think we're almost ready to go. Again, just doing a sound check really quickly. All right. Sorry, I'm just setting up the last few moments here, getting all the little details hammered out. Perfect. All right. Got about a minute here, and just want to see one last thing. I think that's okay. All right. I think we're ready to go. Sorry about all the little setup pieces there. I just want to make sure that I had everything kind of perfect. Now we're ready to go. All right, welcome. My name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. And we wanted to celebrate Math Awareness Week like we do every year. But unfortunately, we've had some little snafus in our healthcare system right now and across the planet. So we haven't been able to do anything on ground. CRC usually hosts an integration bee as a culmination of our Math Awareness Week. And unfortunately, just didn't work out this year. So we decided to still continue the spirit of Math Awareness Week with several different activities that are going on digitally around our campus. And then I'm doing this talk today. I'd like to, again, thank everybody for showing up. Throughout this talk, there will be seemingly mysterious patterns, so much so that it might lead you to think that our topics for today verge on the magical and outline some maybe underlying driving force that directs our future for us or something like that. And in many ways, you would be correct, actually. There is a wizard behind the scenes. And we will take a moment or two to pull back the curtain, so to speak, to reveal the sorcery of this creature. There will be numerous times when patterns will emerge in our talk. These will defy our common sense and confound our logical minds. However, I beg that you keep a sharp wit, a keen curiosity, and an open imagination. Now, not to ruin the story, but the wizard behind the curtain is mathematics, the language and truth of the universe. I have endeavored to keep the level of math required for us to follow our story as attainable as possible. However, as our play progresses, we will venture into arithmetic, algebra, and maybe some light concepts in calculus, but none of these are required to keep your imagination engaged in this talk. I promise that you will be astounded. I guarantee you will wish that this was what your math course covered. For now, our story will begin with one man. Before we get to that, man, I just want to let you know that if you want to join the chat, you can. If you're using a Los Rios Google account, it'll tell you can't log in because Los Rios blocks YouTube as an app. So just sign into your personal account and you can enjoy you can hop into the chat room, or you can just enjoy without chatting. I won't be able to read the chat as I move forward. That's just because I'm keeping track of a lot of different things. So if you're yelling at me for some reason, I apologize. I won't be able to see it. Anyway, back to the show. So our story begins with one man. This man is Fibonacci. Now, I want to mention again, there'll be a lot of patterns. Look for patterns in this entire talk. Okay. So let's start talking about Fibonacci, the man, the legend, the myth. Fibonacci is actually just a nickname. His actual name, well, not really his actual name, but Leonardo of Pisa, same as the Leaning Tower of Pisa. That's where he's from, is the city in Italy. Fibonacci is a shortening of the Latin Filius Bonacci, or son of Bonacci, and he was called Leonardo Pisano, or Leonardo of Pisa. He also sometimes called himself Leonardo Bigolo, or Bigolo means traveler. He was prolific. He was an Italian mathematician in the 12th and 13th centuries. He was also considered as the greatest European mathematician of the Middle Ages. He was prolific with his contributions to mathematics, specifically a beautiful field of study called number theory. His contributions, amongst many other things, but probably foremost in everybody's daily life, is the fact that he introduced the base 10 system to Europe. That's right, the base 10 system, the decimal system, where if you pay $1.85 for something, that decimal place with the 85 cents after it, that's to blame on Fibonacci. Well, it's not to blame, actually, it's what makes our advanced mathematics works beautifully. Before this moment, we were working on Roman numerals, and you have a problem with decimals and Roman numerals. They don't work well together. So Fibonacci did not invent the system. He borrowed this system, but he brought it to Europe. So he is known as kind of the godfather of that. He also wrote some books, specifically the Book of Squares. And there's a lot of stuff he did in this Book of Squares. It was published in 1225 AD, obviously. And among many other things, he started playing with numbers, because the field of number theory in mathematics is very beautiful for most mathematicians. We love number theory. So he started with this very simple process. I wonder what 1 squared is. Well, we know 1 squared is 1. It's not that big of a deal. But then he thought about 2 squared. And now we know when you square 2, it becomes 4. But he wrote it slightly differently. 2 squared is 1 plus 3. And from there, he actually recognized a pattern. If you go to 3 squared, which is 9, he wrote as 1 plus 3 plus 5. You can add those up. 1 plus 3 is 4 plus 5 is 9. Pretty interesting, actually. And you can keep going. For example, 4 squared, which is 16, is 1 plus 3 plus 5 plus 7. Very, very interesting. And like I said, you can keep going. And he was the first to kind of showcase that the number, the natural number n being squared, is just a sum of the first n odd numbers. Now, by the way, if you are thinking about taking a college course in mathematics, this fact you prove in pre-calculus. Before you even get to calculus, you can prove this using your mathematical induction. Okay. Another problem that Fibonacci investigated, and the one that we are going to focus on in this talk, is a very weird problem he proposed or put forward in 1202 called the rabbit problem. And this is, I got to admit, a very unrealistic problem. Okay, so let's investigate the rabbit problem, because like I said, it is actually the focus of this entire talk. Right. So rabbit problem. Suppose you got a pair of baby rabbits and they're put in a field. Okay. Now, again, pair of baby rabbits. That's all we're going to talk about the number of pairs that we have in the long run. So we have a single pair of baby rabbits. And those rabbits grow up about after a month, actually. That's what he's going to suppose for his problem. that they become adults at the age of 1 month. So therefore, they can get together, hook up, and have babies. Now, month 1, there's 1 pair of baby rabbits in the field, and month 2, now they're adults. They don't have babies yet. At the end of that, well, I'll say partway into the 3rd month, they then have babies. So suppose that the female always produces 1 new pair, a male and a female, every month from the 2nd month on. Now, a visual of this looks as follows. The initial month, this guy right here, is when they're baby rabbits. And then they grow up to adult rabbits and they mate. Now, this whole chain in this column right here is just the same pair of rabbits. So that brown white right there with the gray ear on the white rabbit, those are the progenitors of this entire process. They're the Adam and Eve rabbits, if you will, right? So babies here, adults there, then they get to have a baby finally. They continue their lives, but they get to have their pair of babies. Now, don't be freaked out, but their pair of babies are going to hook up. Don't worry too much about that. It's just a fictitious example, okay? The following month, they can still have, because they're adults here, they're consenting adult rabbits, they can have themselves another set of babies. So they do. They have these two babies right here. Meanwhile, their first set of offspring grow up and they start looking at each other. Really brotherly, sisterly love, really weird stuff here. But then the following month, they end up having a pair of babies. Now, if you count the number of pairs, first month there was 1, second month there was 1, third month there's 2 pairs. It's the original and then their offspring. The third month there's the fourth month there are 3 pairs of rabbits, the originals, their offspring, their firstborns, and then their secondborns. Okay. And then so on and so forth. Now, is this realistic? Heck no. This is totally not realistic. But it brings into light a very interesting pattern. And this is what's kind of neat about mathematicians in general. We look at something, sometimes it just doesn't seem like it applies to the real world yet. And then we start fiddling with it, all of a sudden you find uses for it out in the wild. So let's talk about these numbers, those numbers that we listed out right back here, the 1, the 2, the 3, and the 5. Those are called Fibonacci numbers. And those numbers are not the only Fibonacci numbers. So let's figure out what all the Fibonacci numbers are. Well, we already said 1, 1, and 2, and 3, and 5. But look, it's being followed by 8, and 13, 21, 34. So how are these numbers generated is really the question. How do we get these numbers? It's a very simple answer, actually. If you start with 1 pair of rabbits, and the next month they become adults, so there's still 1 pair of rabbits. The following month, if you add the last 2 months there, 1 plus 1, you'll get 2. To get to the next month, again, you add the previous 2 months. 2 plus 1, you'll get to 3. Let's hop forward a little bit, see what I did there. Hop, we're talking rabbits, pretty funny. So let's talk about this 144, where it came from. And that 144 came from the same process. Hop back, add the previous 2 numbers. 89 plus 55 is 144. It's a very simple sequence of numbers that can be generated just by using a little bit of simple arithmetic and adding numbers together and creating this laundry list of numbers. It's not super beautiful to begin with, and I don't expect you to say, wow, I'm flabbergasted by this sequence of numbers. No, you shouldn't be, honestly. You could do this with any couple numbers and start adding them and add the previous 2. But this specific set appears all around us in daily life. In mathematics, just to get a little mathy just for a moment, we would define it this way. We'd say f sub n is the nth Fibonacci number. Like, for example, f sub 5 would be the 1, 2, 3, 4, the 5th. Actually, let's say f sub 6, just because I don't like the fact that f sub 5 is 5. So let's say the 6th Fibonacci number would be called f sub 6. So 1, 2, 3, 4, 5, 6. The 5th Fibonacci number is f sub 6, and that's equal to 8. And that is equal to the sum, that's what the plus is, of the previous two Fibonacci numbers, the fifth plus the fourth. That's the formula for it, but we naturally know how to do it. We would just add the previous two is all we'd have to say, okay? But I'm going to reference this notation a few times throughout this talk. Another thing I need to mention is the whole sequence starts with assuming that the first two numbers are 1 and 1. All right. And by the way, for anybody who loves mathematics, this is called a recursively defined sequence, means that it's a sequence that's based upon previous values in its own sequence. Again, wait for it. There will be something cool in a bit. Now, pay attention to my labeling up here. I like to be funny with my labeling. It's funny to me, at least. This is not the funny one, but they kind of preview where we're going as we move along. So the next slide here tells us we're dealing with some hocus pocus, a lame idea. It's actually not a lame idea. It's a Lamé idea. We're about to talk about a theorem posed by a mathematician by the name of Lamé, but I just thought it was funny because it sounds like lame. Anyway, here's what he proposed. Except for the single-digit Fibonacci numbers, there must be at least 4, but no more than 5 Fibonacci numbers within the same number of digits. Okay, that, if you read that, you might just say, what the heck? I don't really care about that. What does that mean? So let's look at the single-digit Fibonacci numbers. Well, 1, 2, 3, 4, 5, 6 of them. That does not fall into this category because, again, I said except for the single-digit ones. But let's look at the 2-digit ones. Well, there happens to be 5 of those. Let's look at the 3-digit Fibonacci numbers. There happens to be 5 of those. Let's look at the 4-digit Fibonacci numbers. There are 4 of those. Look at the 5-digit Fibonacci numbers. There are 5 of those. And this will go on forever, actually. It is true, it is proven that in any given digit category, so if you look at the 100-digit Fibonacci numbers, there's between 4 and 5 of them. Now, by itself, this is, again, not fascinating. I actually reordered this talk to go from least fascinating to most fascinating. So it gets better as we move along. This is, to me, like somewhat understandable because you're kind of adding previous two numbers. So you're kind of limited to how many numbers you can have in a single digit category. So to me, this seems sort of obvious. Maybe, maybe not. It's not super fascinating though. So I just moved past it. So let's talk about some cryptic repeating digits. So this is going to mimic what a clock does. So a clock repeats, a minute hand on a clock repeats itself once every 60 minutes. Well, guess what? The last digits of the Fibonacci numbers start repeating themselves once every 60th Fibonacci number. So if you start at any Fibonacci number, let's say you grab the 27th Fibonacci number, then 60 Fibonacci numbers later, which is the 87th, the final digit will repeat, and that pattern will repeat. So let me showcase. Here's the first 8 Fibonacci numbers. They're 1, 1, 2, 3, 5, 8, 13, and 21. Notice I've highlighted the final digits there to really make it a little easier to see what I'm talking about. These are the final digits. Now let's look at the 61st through the 68th Fibonacci numbers. And notice their final digits. Now this is actually pretty spooky. But remember, there is a wizard behind the scenes called mathematics. There's a logical reason for this, but it's a bit of a heavy lift for us in this talk. But still, this is some of the fascinating, creepy stuff that happens with the Fibonacci numbers. Oh, by the way, every once in a while, you'll hear this. These are the Fibonacci numbers. So just trying to make sure you're awake, essentially. This is not the only pattern with digits in the Fibonacci numbers. I'm just looking back at the haha funny. Okay, I was just making sure that people were just chatting. Okay, so this is not the only number pattern in the Fibonacci numbers. So if you want to know, like we said, the units digit repeat every 60. The last 2 digits repeat every 300. The last 3 digits repeat every 1500 Fibonacci numbers, and the last 4 digits repeat every 15,000 Fibonacci numbers. Now, the Fibonacci numbers should not give any type of pattern like this, but they are. And by the way, There's also the last 5 digits repeat every 150,000. You might look at those numbers, 1,500, 15,000, and 150,000, and really notice a pattern within there. They're multiples of 100 or multiples of 10 of each other, increasing by factors of 10. But the 60 and the 300 are kind of offsetting that. So a little bit of parlor tricks. Dividing groups by 11. Now, in reality, we're dividing groups of 10 by 11. All the magic that we're going to encounter in this talk is completely explainable through mathematics, but it's still, I love that wizard behind the scenes. It's not going to tell you anything and just let you kind of stare at that for a moment and say, how is that true? So the sum of any 10 consecutive Fibonacci numbers is always, always, always divisible by 11. So if you take the 113th Fibonacci number and add it up to the 122nd Fibonacci number, that's actually 10 Fibonacci numbers consecutive, that sum will be divisible by 11. For example, the sum of the 21st Fibonacci number through the 30th Fibonacci number is actually divisible by 11. Now I'm going to show you something I did on the side here to demystify this. Now I'm not going to reveal a lot of the mathematics that happens in the background in this talk because, one, I don't want to knock you out and put you to sleep. But two, I want you to have a passion for the mysteries and the creepiness at times of mathematics like this. But there is an actual reason. So bear with me while I showcase just a quick, well, maybe 30 seconds or 40 seconds of a proof of why this is true. Please, once I said the word proof, please do not tune out. So here we are. We have 10 Fibonacci numbers. Okay, I just call them G1 through G10 because I'm saying that we have a sequence of 10 in a row. Well, I'm looking at the 10th in that group 1 through 10. We have one of each of them, one of the first one of the second one, all the way up to one of the 10th one of the 9th one of the 8th one. But remember how Fibonacci numbers work. That 10th Fibonacci number, which I'm just calling G sub 10, because it's a general Fibonacci number, is actually the sum of the previous two. So it's actually, that 10th one is just the sum of the 9th and the 8th. So I'll break it apart. And I'll say, you know what? I'm going to steal that 10th Fibonacci number, break it apart, erase it basically, and just say it's the 8th plus the 9th. So now instead of one of the 8th Fibonacci's and one of the 9th, we have two of the 8th Fibonacci's and two of the 9th Fibonacci's. But we happen to know that the 9th Fibonacci is the sum of the previous two. And since we have two of those 9th Fibonacci numbers, I'll break it apart into two of the 7th and two of the 8th. And add those up. Now we have 4 of the 8 Fibonacci numbers and, or I should say 4 of the 8th Fibonacci numbers and 3 of the 7th. Likewise, that 8th Fibonacci number is just a sum of the 6th and the 7th. So we have 4 of the 6th and 4 of the 7th Fibonacci numbers. Again, this is the only proof you're going to see, so don't tune out. Okay. So again, we added just 4. I hope you can see the arithmetic there. 3 plus 4 is 7. And what is that? 1 plus 4 is 5. Now I'm going to say, well, that 7th Fibonacci number, that's the same as the sum of the 5th and the 6th. So I'll break that into 7 of the 5 and 7 of the 6th. So watch that. And this pattern goes on. Now I'm just going to let this roll instead of pausing it. And you can see that 6 breaks into 12 of the 5 and 12 of the 4. Now we have 20 of the 5. And that 20 of the 5 will break into 24s and 23s. I'll sum those up. I have 33 of the 4s and 21 of the 3s. That 33 of the 4s breaks into 33 of the 3s and 33 of the 2s. Add those up. And then the third breaks into 54 and 54. And when you add all that stuff up, wait for it, you have 55 of the first Fibonacci number in that sequence and 88 of the second Fibonacci number in that sequence. Ignore that notation if you don't know that notation, but 55 and 88 are both divisible by 11. So summing up those first 10 led to this. It's 11 times 5 times the first number in that Fibonacci sequence plus 8 times the second number. By the way, 5 and 8 are Fibonacci numbers if you didn't know that. So That is the only, I promise, the only proof that we're going to do here. So this is a pretty rad idea. Now, let's run away from that proof because I don't want to freak you out. Let's start with primeval magic. Primeval, look how I spelled that, primeval, because Fibonacci's numbers, consecutive Fibonacci numbers, are actually relatively prime, which means that if you factor them down, remember your arithmetic class, like 6, the number 6, if you factored it into the prime factors, it's 2 times 3. Those are the prime, that's a prime factorization of 6. So it turns out if you have neighboring Fibonacci numbers, like the 8th and the 9th Fibonacci number, they do not share primes. So neighboring Fibonacci numbers share no other common factors other than 1. And 1, by the way, is not a prime. 1 is just 1. So for example, the 8th and 9th Fibonacci numbers are 21 and 34, respectively, and their prime factorizations are right here, 7 and 3 and 2 and 17. They share nothing in common as far as prime factors. Same thing, if you think I only kept it to low numbers, no, let's go to the 44th and 45th Fibonacci numbers. And again, here's the prime factorization for the 44th. Here's the prime factorization for the 45th. Nothing in common. Pretty interesting. Now, you again probably do not think that's interesting. And by the way, that could be proven in pre-calculus. However, would be super hard to prove in pre-cal. I would probably say do upper division number theory. You can prove it there. Let's go on to some creepier things. Secret addition. So let's suppose that somebody says, hey, you know what? For some weird reason, I got to add up the first 20 Fibonacci numbers. Or better yet, to match my example, let's add the first 5 Fibonacci numbers. Well, there's a trick to doing it. Turns out, if you add up the first n Fibonacci numbers, it can be calculated using the following formula. Now, if you do not know what this symbol is, this sigma right here, it just means I'm going to add a bunch of things together, starting at the first item all the way to wherever you want me to stop. So if I want you to stop at the nth Fibonacci number, I'll add the first plus the second plus the third plus the fourth all the way until I get to whenever you tell me to stop. But it turns out if you add up the first n Fibonacci numbers, it's the same as just saying, hey, the n plus second Fibonacci number is this, and I'll subtract 1. It's better to see this in action. Add up the first 5 Fibonacci numbers, 1 plus 1 plus 2 plus 3 plus 5. Well, you can do that addition pretty quickly. That's 8 plus 2 is 10 plus 2 more is 12. But in reality, I know the 7th Fibonacci number is 13. And 13 minus 1 is also 12. So it's a really cool way to do quick arithmetic. Okay, you don't think that that's cool. I don't blame you because you don't know all the little tricks behind the scenes. But now I'm going to freak you out. Now I'm going to freak you out. Paranormal patterns. All right, here we go. Paranormal patterns. Look at these numbers. That's the 3rd Fibonacci number, the 6th Fibonacci number, the 9th Fibonacci number, the 12th. I hope you see the indices here, 3, 6, 9, 12. They're just every 3rd Fibonacci number. Turns out that every 3rd Fibonacci number is divisible by 2. Now that may not freak you out, and I don't blame you. Until you say, well, if every 3rd Fibonacci number is divisible by 2, what is every 4th Fibonacci number divisible by? Well, here's every 4th Fibonacci number right here. Not every single one, obviously, they go on forever. But here's the 4th, the 8th, the 12th, the 16th. And if you're astute, you can tell me what those are divisible by. They're all divisible by 3. If you do not know that, by the way, the trick to finding out that a number is divisible by 3 is to add its digits together. If the sum of its digits is divisible by 3, the number is divisible by 3. For example, 317,811, add the digits up. 3 plus 1 is 4, plus 7 is 11, plus 8 is 19, plus 1 is 20, plus 1 more is 21. 21 is divisible by 3, so therefore, that number right there is divisible by 3. Well, man, we've just shown that every third Fibonacci number is divisible by 2, and that every fourth Fibonacci number is divisible by 3. What about every fifth Fibonacci number? Now, this should be pretty simple for you to see. Every fifth Fibonacci number must be divisible by, you better believe it. You guys are, by the way, because of my latency, you guys are slightly behind me, delayed, so you're never going to answer me in time. But it's divisible by 5. Now, here's where I'm going to freak you out. Every single Fibonacci number, you better believe it, is divisible by 1. Freaked out yet? Probably not. Every second Fibonacci number is divisible by 1. Freaked out yet? Probably not. Every third is divisible by 2. The fourths are divisible by 3. Every fifth is divisible by 5. Every sixth is divisible by 8. Every seventh is divisible by 13. Every eighth is divisible by 21. Every ninth, every 10th, and so on. Do you recognize these numbers? That's right. Those are the Fibonacci numbers. The Fibonacci numbers are self-similar. This is verging on what we call a fractal pattern. They're self-similar. They actually beget themselves. We started with the sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on and so forth. And we find out that even within those numbers, we see those numbers appear again. You better believe that is cool. But if you don't find that to be cool, I do blame you, actually. That is cool. But let's go ahead and take a look at another hidden structure in a Fibonacci number. Now, the Fibonacci number 89 is actually one of the coolest Fibonacci numbers around. 89 has a lot of patterns to it, but I'm going to work with 1 over 89. This is a finite decimal expansion of 1 over 89. You should probably know that ratios of integers are called rational numbers, and they do have patterns within them. Okay? But the pattern of this is it's equal to 0.01 plus 0.001 plus 0.002 plus plus, and so on. If that doesn't freak you out, I don't know who you are. I feel like a car salesman when I do that. I feel pretty good about that. Anyhow, Fibonacci numbers. Like this stuff is really, really eerie. Oh, see, look what I did there? Eerie 89. So let's take a look at the, again, Fibonacci number. It is a Fibonacci number. The Fibonacci number 89. Let's play a little game. Take any number you want, preferably somewhat small because otherwise you'll spend a long time doing this. But I challenge you to do this. Write down any number you want and sum the square of its digits. And then when I say sum the square of its digits, I mean square its digits and then add them up. And then do the same with the resulting number. Rinse and repeat. The reality is you will either eventually get to 1 or to 89, both of which are Fibonacci numbers. For example, 137. It's small enough that we can do this quickly. Take those digits, 137, and square them. 1 squared, and then plus 3 squared, and then plus 7 squared. If you add those up, you get a beautiful 59. Now, let's say you take that 59, break it apart, and say, I have 5 squared plus 9 squared. Well, that gets you 106. And you say, great, I'm going to break that apart. I'll square the 1, the 0, the 6, and add those up. That'll get you to 37. Break those apart. 3 squared plus 7 squared is 58. Great. Break those apart. 5 squared plus 8 squared. You better believe it. 89. It will always lead you to 89 or 1, both of which are Fibonacci numbers. I certainly hope your mind is somewhat blown. I really don't, we haven't even got to the coolest stuff yet. Now, I also don't want to sell you on some hocus pocus that's not true. Okay, this is all true. Mathematically, very true. Everything I'm talking about here is proven and can be proved. This one, I don't know if you can prove this in a pre-calc class, but these ideas can be proven using number theory and mathematics. But there are other things that will be claimed if you do a search for Fibonacci numbers. You'll see things like Fibonacci numbers, nature's miracle. See what I did there, nature's miracle? Um, so it is true that Fibonacci numbers do occur quite often in nature. It is true that there are a lot of flowers that have 3 or 5 or 8 petals. There are a lot of branch patterns in nature that follow the Fibonacci numbers or the Fibonacci sequence. You do see them all the time. However, I do not want to lie to you. I don't want to tell you it is always true, because it is not. There are a bucket load of different types of flora out there that do not have Fibonacci number petals or seeds or something like that. But you'll still see quite a few. There's a propensity of Fibonacci numbers that do occur in nature. And because I just said Fibonacci numbers, you better believe we're going to put down the Fibonacci number right there. They also are claimed to appear in seed patterns. So if you take a look at the seed patterns of this flower, you'll see 2 spirals, one to the left and then one to the right. And if you have the patience to count up those spirals going to the right and going to the left, you will find one going to the right is 34, the other going to the left is 55, and those are Fibonacci numbers. So it is very interesting. It is, again, not always true. So please do not say, hey, Professor Simpson at CRC told me that nature is all Fibonacci. No, it's not. Although there is a lot of Fibonacci in nature. You also see stuff like this. And by the way, I've done this example. I've brought into class, because I love pineapples. I brought into my classes a pineapple and counted up the cross sections. And they are, for the most part, you can get them to be Fibonacci. They're hard to count though when they get to the top. But there are Fibonacci numbers that occur in pine cones and external structures in nature. So because I said that, Fibonacci numbers. Okay, I promise it's going to be a while before we hear that explosion again, so you can turn your speakers back up. All right, so let's step out of this just for a moment, and let's look at a spiral. Let's spiral into chaos. Now, you probably have seen some patterns like this before, because they'll be in textbook covers and stuff like that, but nobody really tells you why they're there. These are golden spirals, and it has something strongly to do with the Fibonacci sequence. And so rather than me describe it, I actually just went ahead and did a GIF of myself, or a GIF, whichever you prefer, of actually developing one of these spirals. So let's take a look. You take a 1 by 1 square and you add another 1 by 1 square to it. Again, 1 and 1 are both Fibonacci numbers. And then I'll attach a square off to the right-hand side of that, which has to be of size 2 by 2 because it's attached to that. So 1, 1, and 2, all 3 of those are Fibonacci numbers. Then I'll attach to that another square, but it'll have to be a 3 by 3 because, well, I'm attaching it to that. So we have a 1, 1, 2, 3. Then we're going to go ahead and attach to that another square, which, by the way, is a 5 by 5. 1, 1, 2, 3, 5. And another square. This will be an 8 by 8. 1, 1, 2, 3, 5, and 8. And finally, the last one I'm going to do here is a 13 by 13. All of those are Fibonacci's. What you do in this game is you start with your smallest square, the first one you drew. In one of the corners, I just start in the upper right-hand corner. I put a little red dot there. And now I'm going to swoop to the opposite corner using a curve. And then I connect opposite corners using a curve. And this is called the golden spiral. Some people call it the Fibonacci spiral. It's the golden spiral. And again, these are all 1 by 1s, 2 by 2s, 3 by 3s, 5 by 5s, all Fibonacci numbers. I don't know why my ink went to blue there, by the way. So you can just ignore that. But all of those are, I lied to you, that explosion was happening sooner than I thought, Fibonacci numbers. That does get mentioned all over the place. You'll see it in like Da Vinci Code and movies all the time, that you'll see this golden spiral. Okay, so now we're going to take what is called an aside. My students who have had me as an instructor for years know that I like asides. I like to talk about things that happen outside of the topic we're within. And so the aside I'm going to talk about here is something that's super awesome for algebra students called Pascal's Triangle. Pascal's Triangle is this guy right here. It's you start with a 1 and a 1 and a 1, and then you so top row is 1, second row is 1 1, third row I have 1 2 1, and you might wonder why did I write a 2. The reason why you write that 2 is because it's a sum of the two ones above it, and then you go down and you have 1 3 3 1, and again the reason why it's the threes are there is because it's a sum of the 1 and the 2 above them. And you can build this triangle forever. It goes forever and ever and ever. It's not that big of a deal, but it does go on and eventually presents you with Pascal's actual triangle. And yes, I wrote that out by hand. And yes, it took a very long time. Not forever, but it took a long time. You can see the sum of the two numbers above gives you the diagonal element 2. If I went to this element 70 here, it's a sum of 35 and 35. If I went to 210 here, it's a sum of 126 and 84, and so on and so forth. Now, before I go any further, I just want to tell the students who are in algebra classes right now why this triangle is so awesome for you. The reason why, and if you're in calculus, you already know this, the reason why it's awesome is because it gives you the expansion of binomial powers. I'm going to let this go just until I get to the square, and then I'll actually highlight what I'm talking about. So I'm writing a plus b quantity squared, and now I'll just say that's 1a squared plus 2ab plus 1b squared. That's supposed to be n with squared. There we go. So it tells you the coefficients. A plus b to the 0th is just 1. A plus b to the first is 1a plus 1b. A plus b squared is 1a squared plus 2ab plus 1b squared. And a plus b to the third, which I'm writing in here, I'm not actually writing it now, I wrote it earlier, is 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And this pattern goes on forever. It's a fast way to multiply out a binomial like that. So if you've never seen it, man, you would be light years ahead in an algebra course by doing that. Let's go back to this triangle because I want to actually showcase why this triangle is in this talk. Because this talk is about the Fibonacci numbers and about chaos and about the golden ratio. And you're wondering, where's my chaos and where's my golden ratio? I want chaos, darn it. And I want my Fibonacci numbers. We can get the Fibonacci numbers by taking that triangle and sliding each of those rows all the way over to the left. Watch what happens. I'm going to take those rows and slide them all the way over to the left. Be vigilant. Watch what happens. I'm sliding them over to the left. Here we go. Here we go. Now you're going to highlight the diagonals. And then you're going to add them up. The first diagonal, wait for it. First diagonal adds to 1. Then 1, then 2, then 3, then 5, then 8, then 13, then 21, then 34, then 55, and 89, and so on and so forth. What is going on? Fibonacci numbers are going on, folks. That is rad. Let me just tell you why that's rad. Because this whole topic about Pascal's triangle was an aside. I never said anything about Fibonacci numbers once I got to the Pascal's triangle. I just said, hey, here's a cool triangle. Oh, by the way, it's related to algebra. It helps us multiply out a plus b quantity squared or a plus b quantity to the 5th power or something like that. But all of a sudden, you do a little geometric slide and you get the Fibonacci numbers. Now, this is starting to be freaky because they're starting to creep into other realms of mathematics. And now for some chaos. Time for some real chaos. You probably wondered why I highlighted all those numbers red. Something about all those numbers that should ring true to you is everything single red number there is even. So if I block out all the even numbers, look what happens. Again, even numbers, block them out. Even numbers, block them out. That's way fun. It took me a lot of aligning to do that. So it almost looks like a jack-o'-lantern, right? So there are some triangles in there that appear when you block out the even numbers. Now, I hope you're ready for some awesomeness because we're going to play a game of chaos. Label 3 vertices on a triangle, red, blue, and green. Doesn't really actually matter. We're going to plot a point at random, in or out of the triangle, doesn't matter. And we're going to roll a die or spin a dial. And if that, we're just going to spin a dial, honestly. But if we spin a dial and it lands on red, we're going to go half the distance between our plotted point to the red vertex. If it goes to blue, we go half the distance from our point to a blue vertex, and so on and so forth. Now, let me go ahead and share this because I have this ready to go. Here we are. Share away, Roy. There we are. I'm going to wait a moment because I want YouTube to catch up with me. You'll hear me be silent. I'm sorry. I'm just waiting for YouTube to catch up because I want to make sure that you can see this. Yes, you can. Okay. So now here is the game. I've got 3 dots, red, blue. Oh, sorry, that was green, wasn't that? Red, green, and blue. I have a random point in the center. Now all I'm going to do is spin this dial. I spin the dial. It goes to green. So I'm going to go half the distance from my black point to the green point. Then I'm going to spin the dial again. It lands on blue. I'll go half the distance from that new green point to the blue point. And then I'll just click fast so that now I just click this and I keep repeating that. And you say, well, that's a boring game. Well, great. Let me go by tens then. I'll just do 10 rolls at once. And you say, well, that's no fun. Go by 100. Great. I'll go by 100. And you say, that's no good. Go by 1,000. I'll go by 1,000. Folks, this is called chaos. Welcome to it. This picture that you're looking at right now is called Sierpinski's triangle. It is a visual representation of chaos. It is also a visual representation of a fractal, a self-similar shape. So if you look at that, your mind should be blown, by the way. If your mind is not blown, you have failed this talk. Your mind should be blown. You could go ahead, you could totally go ahead and try this as an experiment, but you see how many thousands I clicked there, so that would be a while. But this is a fractal, and what fractals are is they're self-similar shapes. So if I look at this triangle and I say, man, I want to zoom in to that red triangle, which I can't. I've zoomed in as much as I can. But if I want to zoom into that red triangle and blow it up, it would look just like this triangle we're currently looking at. And if you were to go into the upper part of that red triangle and zoom in on that, it would look just like the triangle you're looking at. That is a fractal. And now if you just spend a moment staring at that, then I'm going to bring you back to our talk. I'm just getting my stuff back to the talk as well. And I'm going to go back to the picture here, and you should notice this is the same picture as that fractal game. It turns out that Pascal's triangle, when you remove the even numbers, gives you a fractal and introduces you to chaos. What is going on? I'm hopping back over because I want to see if people's minds are blown. Thank you. Thank you, Brandon, for saying your mind is blown. I love it. Thank you. All right. So I needed that confirmation. So mind is blown, right? Well, let's just reflect just for a moment what we have just done. We started with the Fibonacci numbers. We found all these cool little patterns within the Fibonacci numbers. And then we took an aside and said, let's introduce ourselves to Pascal's triangle, this guy right here. And we noticed that when we slid things back on Pascal's triangle, we got the Fibonacci numbers again. And then we said, well, let's go ahead and deal with Pascal's triangle again, but remove the evens, and we got chaos, a fractal. So this aligns or connects Fibonacci numbers to fractals, to Pascal's triangle, to algebra, to chaos. And now we go into the golden mystic. By the way, that's a Van Morrison song, Into the Mystic. I just had to put it in there because Van Morrison's awesome. So on the left-hand side, you see some of the Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13, and so on and so forth. If you start taking ratios, so for example, the ratio of 1 divided by, or the fraction 1 divided by 1, well, we know what that is. It's just 1. If I hop over to 2 and I say, what's 2 divided by this neighboring 1? That's just 2. If I hop over and say, what's this 3 divided by that neighboring 2? It's 1.5. What if I said 5 divided by 3? 1.666, and so on and so forth. What about 8 divided by 5? And so on down the line. What if I keep doing those divisions? You should notice that the ratio, the decimal expansion of the ratio, and by the way, when I say is, it should be is approximately. But as I'm getting that ratio, you should notice that it is converging to something. It's getting closer and closer to 1.61, maybe 8 or something like that. And it is. As n goes to infinity, so as we look at the numbers down the line in the Fibonacci sequence, the ratio of the next term in line to the current term is approximately 1.618,033,98875. And by the way, this is not a property of Fibonacci numbers. By the way, if you hear my chair squeak, it's because I like to stand. I get really excited at this point. I like to stand because I'm like a little kid in a candy shop. All right. So this ratio 1.618,033,98875 is not begotten just from the Fibonacci numbers. Start this sequence with any two numbers you want, 3 and 7. And you say, I have 3 and 7, and then you add those together and you get 10, and you add 10 and 7, you get 17, and so on and so forth down the line. And take those ratios, it will always be this special number. So let's talk for a minute about the last half of this talk, or the last part of this talk, I should say. It's not really the half, but we're going to talk a little bit about the golden ratio. I'm going to leave you on a cliffhanger with that episode. We're talking about the golden ratio. Now, the golden ratio, I took quite a bit out of this talk, to be very honest with you, because there's so much to talk about with Fibonacci's and the golden ratio that it's very difficult to compress it into a single talk. So the only thing I left in there is this: a number by any other neighbor. So all the names for the golden ratio, which we haven't talked about yet, but we will right now. It's called the golden ratio, the golden mean, the golden section, the golden rule, number, proportion, cut, divine proportion, divine section, the mean of Phidias, or just plain cool. This number has been known for quite some time, the number we're about to derive. And the derivation is the second part of little bit of math that we have to do here, but very little bit. The golden ratio, or the golden cut, this problem was posed by Plato way back in the day, because Plato's OG. He posed the following question: I would like to know what's the special cut in a rod where the ratio of the overall length of the rod, this length right here, the ratio of that long length is to this long cut, is the same as the ratio of this greater cut to the lesser cut. And so I wrote this up as an algebra problem, actually. And instead of using X's, because everybody's using X's these days, that's such a popular letter, that I just decided to go with an unpopular letter called phi. It's a Greek lowercase phi. So I just said the longest length, the bar itself, is 5 + 1 units long. Why did I say +1? Because I wanted to. It made the math easy, and I thought, you know what? My audience might not want the math to be terrible, so I'm going to make it to where the math is somewhat easy. The proof is the same no matter what you do, but this makes the math a lot easier. So we want the ratio of this whole length to this greater length, so 5 + 1 to phi, to be the same as the ratio of the greater length, phi, is to the lesser length, 1. So we want these two fractions to be equal. Welcome to algebra. Multiply both sides by phi, and you get that bad boy right there. And then subtract phi + 1 from both sides, and you get that bad boy right there. And you say, I remember the quadratic formula. So I'm going to go ahead and use the quadratic formula because I know the quadratic formula will tell me that phi is the opposite of b plus or minus the square root of b squared minus 4ac, all being divided by 2a. Now, you don't have to know that, but it becomes this. Now, before we continue, I want to just tell you, phi is a length on a bar here. If you look at 1 minus the square root of 5, square root of 5 is slightly greater than 2. 1 minus a number slightly greater than 2 is negative. Divided by 2, it's still negative. So I'm going to throw out the negative version of this answer because it's not realistic. So if I keep the positive version, what the cut? What do you think that number is? It's from the ratios of the Fibonacci numbers. That is the golden ratio. It's from the ratio of the Fibonacci numbers, technically the ratio of any sequence of numbers, but whatever, any sequence where the last two numbers get added. But we developed it from the ratio of Fibonacci numbers. So now we have glued the Fibonacci numbers to the golden ratio. They are intimately tied together, by the way, because there's going to be some really cool stuff coming up. All right. Notice, by the way, I use gold for the phi because phi is pretty awesome and it's golden. All right, let's talk about the diabolic decimals of phi. Now, here's where it ramps up. Here's where my mathy folks who are in the audience are going to go, what is going on? First, to remind you, phi is roughly 1.618, yada, yada, yada down the line. That's the lowercase phi. The uppercase phi would be that phi minus 1. We're going to define the uppercase phi to be phi minus 1. Well, obviously, if you subtract 1 from 1.618, it's just 0.618. There should not be any craziness there. That's okay. What is crazy? Capital phi is just a reciprocal of little phi. Therefore, little phi is just a reciprocal of capital phi. That, to me, is pretty cool. But if that doesn't blow your mind, that's okay. I got some other stuff for you. Well, how about some powerful magic? Powerful. See what I did there? Because for even integer powers, the following returns a whole number. Now, you may not think that's fascinating until I tell you this. Phi is an irrational number. Phi is irrational, which means phi itself is a non-terminating decimal. It goes on forever. There's no patterns within it. And yet, if I raise it to an even power, and add it to 1 over phi to that same even power, it becomes a whole number. Not just a rational number, but a whole number. And by the way, for odd powers, the difference returns a whole number. Okay, if that doesn't stoke your curiosity, then I'm going to blow your mind. Because phi has a fascination with phi. See what I did there? Phi and phi. All right, well, phi is about fives. Phi is equal to 0.5 times 5 to the 0.5 plus 0.5. Well, that is true because of the fact that it's 1 plus the square root of 5 over 5 or over 2. So that's okay. But it's also equal to 2 times the cosine of pi over 5. You probably didn't know that. But not only does phi have a fascination with fives, the golden ratio has a fascination with fives, but it's also a bit fiendish. It's fiendishly complex. Why? Because phi is equal to negative quantity sine of 666 degrees plus the cosine of 6 degrees times 6 degrees times 6 degrees, which also is equal to negative 2 sine of 666 degrees. Now remember where we have come from. Very difficult in mathematics to remember because you're doing a lot of stuff in mathematics. Things get jumbled. But remember where we started. A simple sequence of numbers. 1, 1, 2, 3, 5, 8. And here's where we are. The sorcery of phi. So remember, it's fiendishly complex, but at the same time, it's simultaneously a sinh because phi is equal to e to the arcsinch of 0.5. That's a hyperbolic, the inverse hyperbolic sine function, by the way. If you don't know that, that's all right. Phi, okay, so if you're going to be blown away by anything, if you're just one of those people that's just like never satisfied, you just look at the world and go, yeah, whatever, whatever. You know, I could say I don't have anything for you, but I do. Phi is the root of all Fivel. Phi is actually equal to the square root of 1 plus the square root of 1 plus the square root of 1 nested throughout on forever. If you don't believe me, well, seeing is believing. Here is me doing Desmos yesterday. Square root of 1 plus, now watch over to the right hand side. I'm going to just keep adding square roots of 1 underneath there. You better believe, if that doesn't blow your mind, get out. Just get out of my classroom. That is too rad. But let's go ahead and look at ritualistic ratios of phi. Phi is actually equal to 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 on forever. But again, sometimes seeing is just believing. So we'll do 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, and so on and so forth. And you will see that ratio tends to the golden ratio, 1.618, yada, yada, yada. Which I was pretty impressed, by the way, that Desmos does this much. Usually it won't, but I can break Desmos. I've broken it several times. Otherworldly patterns. Now, what I'm about to show you is really, really neat, like everything else. Phi, when you square it, becomes 1 phi plus 1. That may not blow your mind, but phi, when you cube it, becomes 2 phi plus 1. Phi, when you raise it to the fourth power, becomes 3 phi plus 2. To the fifth, 5 phi plus 3. To the sixth, 8 phi plus 5. To the seventh, 13 phi plus 8, and so on. What are those? The Fibonacci numbers. So again, so I told you earlier that we developed phi. We said, oh, let's take the ratio of the Fibonacci numbers. And I said, this becomes 1.618, yada, yada, yada. But you could develop that same ratio using any sequence, starting at any two numbers and just adding like the Fibonacci's forever and ever and ever. You'll still end up with the golden ratio. But there's something very intimately tied between the golden ratio and the Fibonacci numbers because of this specific pattern. So we started the talk today. This little simple sequence of numbers, 1, 1, 2, 3, 5, 8, and so on and so forth. We've led ourselves to Pascal's Triangle, to weird patterns with Fibonacci's, to chaos, to algebra within Pascal's Triangle, to the golden ratio. And now we round it out with some visual effects. Well, maybe not, but spellbinding visuals that we have with the golden ratio itself. So experimentally, it has been shown that the most pleasing rectangle to the human eye, at least in this list, is the one that's the most golden, the 21 by 34. And if you look at your credit cards, that's not mine. You can't use that number. It expired in 2002. So anyway, if you look at your credit cards and measure them out, they're nearly golden in ratio. Length, the ratio of length to width, or length to height, I guess you should say, is roughly 1.6, very roughly 1.6. It's been used in structures all throughout history, just because it's naturally pleasing, not because there was some Illuminati thing going on, but because it's pleasing to the eye. The ratio of height to width being 1.618. This right here is actually the one on the left is the UN building. This picture is not from my old apartment, but my old apartment faced this. So I know that structure very well. But the floor patterns on these are actually Fibonacci, or I'm sorry, golden ratios. And by the way, you can see within the Parthenon here that there's something like a Fibonacci spiral in there. And also there are ratios, specifically this upper corner, that are golden. It's hidden in imagery. So you will see it in photography a lot. Actually, if you have a camera that allows you to put on, I forget what they're called, like little sections like that, they're golden sections. So the way that you take pictures, right? Golden. It's hidden in the Mona Lisa. Probably not purposefully, but it is. It's hidden in our bewitching bodies. The ratio of your height to the length from your feet to your belly button is actually the golden ratio. So it is really, and by the way, it's everybody's slightly different. Okay. But it's really very interesting how it does actually occur in nature. And it is used in marketing. I'm not going to stay too long on that image because I don't want to be taken down. And finally, it's been used in economics. Ralph Elliott authored The Wave Principle, a book uncovering many patterns in the stock market based upon the Fibonacci sequence and the golden ratio. These are now used and have been further augmented to predict market patterns. Using these techniques, Elliott, without the aid of any computers, successfully forecasted the end of a bear market decline from 1933 to 1935 to the exact day. So what I really want to drive home here is I want to stoke your curiosity. I want you to really see the passion that your professors have for mathematics because we get to see behind the curtain. And often it is the case that when you get to see behind the curtain, it ruins the show for you. Like if you ask anybody who does anything in cinematography or anything in photography or something like that, if they work in that industry, they can't watch a movie without dissecting it. It's because they're spoiled. Somebody has revealed the wizard behind the curtain. But there is still a power to that. And believe it or not, your math professors are still wonderfully fascinated by the beauty of mathematics behind the scenes and in nature. I don't want you to run out of this talk saying, hey, guess what? Everything's Fibonacci, because it's not true. It is not true. But I do want you to go out with a new appreciation for it. I really appreciate you taking your time away from your crazy life right now. I hope everybody's safe. I hope you enjoyed the talk. And I really, really, really sincerely hope that you have a wonderful rest of your semester, rest of your year, and that I see you guys in the fall, or one of us on our campuses see you in the fall for a new start, a new beginning. Thank you very much. Have a wonderful, wonderful afternoon. And yeah, thanks for attending. I should say this talk is being saved, and I'll go ahead and post it up in the uh, I'll post it to your professors. Thank you, Marcus. All right, now I'm stepping away. You guys have a wonderful day.